Okay, so this may be a bit longer than some of the videos. It's going to be fairly involved. Look specifically here at finding the zeros of a polynomial function. Look specifically at the polynomial function you see here, p of x equals x to the 7th minus 5x to the 6th plus 4x to the 5th plus x to the 4th minus 5x to the 3rd plus 4x squared. So this is a 7th degree polynomial function. We talk about the zeros of a function. The zeros of a function are the values that make the function equal to 0. So normally, 0 is not a zero of a function, though in this particular case it is, because if you plug 0 in here, you would have 0 to the 7th, to the 6th, the 5th, 4th, so on and so forth. Should be fairly obvious that if you plug in 0 as the input, the output also is 0. And so that's what we mean by a 0. If the output is 0, then we call the input a 0 of the function. So again, the 0 is not necessarily 0 and usually isn't 0. But 0 is a 0 in this case. There are other zeros. We'll talk about that in a moment. I just want to say a little bit about the fact that these zeros are also referred to as, well, they correspond to, for graphing purposes, to the x-intercepts, because if the function is 0, it follows that the y value for the graph would be 0. And if that's the case, well, that's the x-intercepts. If y is 0, then we're on the x-axis. These would be the places where the graph crosses the x-axis. And typically when you're looking at graphs, the x-intercept or intercepts and the y-intercept or intercepts, if it's a function, there's only going to be one y-intercept, though there could be lots of x-intercepts. But anyway, those are often of interest for graphing purposes, and if it's based on a real application, a real-life application, then often those zeros will be the places where either x is 0 or y is 0 are going to be important parts of the application. Not always, but frequently. Now, in the history of polynomials, linear polynomials in one variable will have a solution in most cases, just one solution in most cases. There are sort of special cases that we don't need to worry about that right now. And you should be familiar with finding the solutions to a linear equation. That's one of the first things that's learned in algebra. And you should also have learned how to solve quadratic equations, possibly by factoring, completing the square root property sometimes, and the main way, because it always works, the quadratic formula. So for first degree linear, they're a method for finding the solutions to an equation. And those solutions to the equation correspond to the idea of the zeros of a function, a linear function. 0 is a matter of, if you have y equals 5x minus 2, then you're solving that equation to get x equals, I guess, I guess it would be, what did I say? Be 2/5, right? And there's only one solution. Quadratics, often two solutions. And the quadratic formula will find those. Third degree was a bit of a challenge to find a general method for. Back in, I think it was actually, was it the 14th century? You can do some research on that if you're interested, but it's, anyway, for a long time it's been known how to solve third degree equations. And I think the fourth degree or quartic equations were actually solved in a general technique even prior to cubic or third degree equations. So anyway, by like 1400, if not before, it was known how to solve first degree, second degree, third degree, and fourth degree equations in algebra. And for several centuries thereafter, people tried to find the general method for solving a quintic. By a general method, what I mean is something like the quadratic formula. So a quintic or fifth degree equation turns out does not have a general technique that you can apply in every case. There are fifth degree equations you can solve, certainly. If I wrote down x to the fifth equals 1, well, one of the 5 solutions to the equation x to the fifth equals 1 would be x equals 1, because obviously 1 to the fifth power is 1. The other 5 solutions I'm not going to go into right now. Excuse me, the other 4 solutions I'm not going to go into right now, but there are 5 solutions. One of them is x equals 1, if x to the fifth equals 1. And the other 4 solutions, I believe, are, yeah, I'm pretty sure, yeah, they'll be complex, non-real complex numbers. Okay, so anyway, back to this polynomial here. P of x equals x to the 7th. I mentioned there is no general technique for finding a solution for a fifth degree equation. When I say general, what I mean in all possible cases. There are special ones you can solve. And the same thing applies to 6th degree, 7th degree, and beyond that. So in general, there's no solution, but there are special cases like the one we're going to be looking at here where you can actually apply algebra to find the solutions. A 7th degree polynomial can have as many as 7 zeros. So if I write down the equation p of x equals 0, there could be as many as 7 different solutions to this. What we're going to find is that there's actually only 6 solutions, and only 4 of those are real numbers. But I'm getting ahead of the story here. Anyway, there are other zeros. 0 is a 0, as already mentioned. There are other zeros. If you plug in 1, p of 1 equals, like I copied and pasted and didn't fix something there, so let's fix that. P of 1 is 1 to the 7th minus 5 times 1 to the 6th plus 4 times 1 to the 5th, and so on and so on. And so that works out to be 0 in the end. P of 1 is 0. You can finish the arithmetic here. Just check it real quick in your head. Okay, so we found 2 zeros. 0 is a 0, p of 0 is 0. 1 is a 0, p of 1 is 0. Now I'm going to find the other zeros here by applying a few different techniques. First of all, we can factor x to the 7th minus 5x to the 6th plus 4x to the 5th plus x to the 4th minus 5x to the 3rd plus 4x squared by noting that x appears in every term, and actually x squared or higher appears in every term, which means that x squared is a factor. So if I factor out the x squared, we have p of x is x squared times a 5th degree polynomial, which I won't bother to read out. It's right there for you to look at. Okay, so if we go back and think about p of 0 and p of 1, which I just, looks like I made that same mistake here. Fix that real quick. Okay, I think that's fixed now. If we look at p of 0, we look at the factored form, x squared times the 5th degree or quintic polynomial here. Well, if you plug in p of 0, we would have 0 squared, x squared, times all this other stuff. All the other stuff works out to be 4 in the end, but 0 times 4 is 0. Of course, we knew that p of 0 was 0, so we didn't learn anything new here, but maybe get a little bit of an idea as to how that's working in terms of the factors, how the factors relate to the zeros. If we look at p of 1, it's a similar story, but in this case, 1 is x, so we have x squared, 1 squared, times this thing here, 1 to the 5th minus 5 times 1 to the 4th, plus 4 times 1 to the 3rd, plus 1 squared, minus 5 times 1 plus 4. Anyway, all of that stuff turns out to be just 0. 1 minus 5 is negative 4, plus 4 is 0, plus 1 is 1, minus 5 is negative 4, plus 4 is 0. So in the case of p of 1, if you look at it in terms of these two factors, we have p of 1 is 1 times 0, which is 0. Are there other zeros? Yes, there are, and as I already mentioned, a 7th degree polynomial can have as many as 7 zeros. For graphing purposes, it turns out that amounts to saying that a 7th degree polynomial can cross the x-axis as many as 7 times. I'm going to mention that it also turns out that a 7th degree polynomial can change directions as many as 6 times. It can have 6 what are called turning points, places where the graph was going up and then changes direction, goes down, or vice versa, is going down, changes direction, and starts going up. Maybe come back to, well, I'll come back to that at some point, maybe in this video. But worth remembering, the number of zeros or x-intercepts, the maximum is the same as the degree of the polynomial. It could be fewer than that, but it cannot be more than the degree of the polynomial. And the number of turning points, the maximum is 1 less than the degree of the polynomial. It could be less than that, but it cannot be more than that. So at most 6 changes of direction for this particular polynomial. Okay. Okay, come back and look at the factored form again. So we have 2 polynomials, x squared, which is basically about as simple as it's going to get, and then we have this 5th degree polynomial. Now, because of the fact that 1 was a 0, we know by something that's called the factor theorem that because 1 is a 0, that x minus 1 is a factor, that it will divide into that. And that's exactly why p of 1 becomes 0, because, as we'll see a little bit later on, x minus 1 is a factor, and if you were to plug in 1, we'd have 1 minus 1, which is 0, and the whole thing goes to 0. To get to that, we have to apply, I'm going to apply something, don't have to, there's other ways of thinking about it, but what I'm going to do is apply what's called long division. It's kind of similar to the division that you learned with integers back in elementary school, but it's applied with polynomials. Excuse me. So what I'm going to do is divide x minus 1 into the polynomial x to the 5th minus 5x to the 4th plus 4x cubed plus x squared minus 5x plus 4 that we see here. The process is actually fairly simple, but it's easy to make mistakes here also. It really just amounts to a little bit of multiplication and addition and subtraction, and as long as you're careful about it, check your work, it should go okay. Okay, so you write the divisor, the x minus 1 out here. The thing's being divided, the dividend I'm putting inside of a division box here. And then we are going to repeatedly do divisions here. So you're going to see this several times here. I start by looking at the x from the x minus 1. Normally I want this written in descending order. Likewise, whatever's in the dividend here should be in descending order. Power is getting smaller as you read from left to right. And you start by just taking the x here and comparing it to the x to the 5th. You ask yourself, well, what should I multiply x by to get x to the 5th? And the answer is x to the 4th. So up in the quotient area here, I write x to the 4th. Doesn't really matter too much where you put it, but it's often suggested you just write it above the x to the 4th here, sort of create an x to the 4th column. That's the key here, is keeping things lined up in columns. So we have x to the 4th, then we multiply it out. We have x to the 4th times the whole x minus 1. That's where I'm getting the x to the 5th minus x to the 4th. X to the 4th times x is x to the 5th. X to the 4th times 1, negative 1, negative x to the 4th. And then, just as in long division with integers, we then subtract this from the original dividend, and that gives us the remainder of the first division. And then we're going to divide repeatedly until we get to what we want. So we subtract x to the 5th minus x to the 5th is nothing, so don't see any x to the 5th term down here. And then this we have to be careful. We have negative x 5x to the 4th. Here we have a negative x to the 4th. But keep in mind that I'm subtracting. Sometimes people will actually just change the signs here and add, and it works. There's different. Sometimes people write this in parentheses and put a negative out in front of the whole business. That works also. I just remind myself that I'm subtracting. So we have negative 5x to the 4th. We're subtracting negative x to the 4th, which means I'm going to add 1 x to the 4th to the negative 5 that we already have here, which gives me negative 4x to the 4th. mistakes that are made are usually in that subtraction step here. I didn't write anything down here because didn't get any terms here because we're just multiplying x to the fourth times two terms. So we only get two terms. So here you could think of subtracting nothing from these things, which means we just bring them down. Okay, so that was the first division. Then you just keep repeating here. I copied this and we'll go to the next step here. Okay, so for the next step, we had this remainder, which is our new dividend, our new divisor. So this was the remainder from the last step. This sort of the starting point of our next step. So we do the same thing that was done before. I look at the x over here. I compare it to the negative 4x to the fourth and say, what would you multiply x by to get negative 4x to the fourth? The answer is negative 4x to the third. So we have negative 4x to the third times x, which gives me negative x to the fourth, negative 4x to the fourth here. We get negative 4x to the third times negative 1, which gives me positive 4x cubed. And then we subtract, and since these two terms are the same as those two terms, when you subtract them, we end up with nothing there. And so it just brings down all the other stuff. You keep repeating this process until you end up with a remainder which has a degree lower than what you're dividing by. So we can keep going. So x goes into x squared. So next step, you look at the x, you look at the x squared. It's actually this x squared here. And the x squared minus 5x plus 4. So x goes into x squared x times. So I wrote plus x up here. X times x minus 1 is x squared minus x. We subtract, again, it's negative 5 minus negative 1, so that's negative 4. And then this 4 is just brought down because nothing's being subtracted from it. And so this is our remainder from that step, negative 4x to the fourth. We will then do one last division, x minus 1 into that. It goes negative 4 times. Negative 4 times x minus 1 will give us that thing. So put a negative 4 up here in the quotient area. Negative 4 times x minus 1 is negative 4x plus 4. Subtract and get a remainder of 0. The reason we get a remainder of 0 is because x minus 1 divides evenly into x to the fifth minus 5x to the fourth plus and so on. And I knew it would divide evenly, which is why I divided. We will be seeing other divisions later on, but, or at least you will in your homework. But this is a particularly useful division because it allows us to actually factor this x to the fifth minus 5x to the fourth plus and so on. Because it turns out that that fifth degree polynomial is equal to x minus 1 times the x to the fourth minus 4x cubed plus x minus 4. So the whole idea of this division is that if you multiply this and that together, and then if you add the remainder, which in this case turned out to be 0, it will give you the original dividend under the division symbol here. So I should have that written down here. Okay. So this is what I was saying. X minus 1 times x to the fourth minus 4x cubed plus x minus 4. So that's the same thing what we ended up with here. That times x minus 1 is equal to the x to the fifth minus 5x to the fourth plus 4x cubed plus x squared minus 5x plus 4, which was our dividend here, which came from the original p of x once we factored out the x squared. The x squared is still important. We'll get back to that, but we don't need to worry about it right now. We're analyzing. We're just taking the pieces that we just can deal with and working with those, and we'll put the whole thing back together later on. Okay, so I have two factors here, x minus 1 and the fourth degree or quartic four-term polynomial here. Lots of fours going on. It turns out that factors, you might look at it and kind of see the pattern. Could have actually maybe seen the pattern way up here. X to the fifth minus 5x to the fourth plus 4x cubed. 1, negative 5, 4 coefficients. Here, 1, negative 5, 4. Same coefficients. So should maybe go back and think about that and see how you could have factored out the x squared minus 5x plus 4 back at that stage. But if you don't want to think about that, you don't need to. Okay, so anyway, back to this thing. This has 4 terms. There is a pattern to it. Coefficient of 1, coefficient of -4, coefficient of 1, coefficient of -4. If I'll apply what's called factoring by grouping. So I'm looking at the first two terms here, x to the fourth and -4x to the third. We can factor an x cubed out of those two. The x minus 4 is irreducible, but I can factor a 1 out because a prime can always, or irreducible thing can always be written as 1 times itself. And it's not normal to factor out a 1, but sometimes it's useful, and this is one of those situations where I think it's useful. So if I factor out the 1, well, you notice we've got x minus 4 in both places, and if you remember factoring by grouping, I can then use the distributive property to factor that x minus 4 out. So we have x cubed plus 1 times x minus 4. By the way, the x minus 4 tells me that 4 is a 0 of the original polynomial, because we just discovered that x minus 4 was a factor of the original polynomial. And if you plugged in 4 into the original, you'd have 4 minus 4 right here, which is 0. Doesn't matter what anything else is, because 0 times all the other stuff would just be 0. You may recall that x cubed plus 1 factors. Difference of squares will factor, difference of cubes will factor, and a sum of cubes will also factor. So the factorization of x cubed plus 1 is, well, first of all, we take the cube roots. We have x plus 1, the binomial, and there's a trinomial, quadratic, trinomial in this case, which is x squared minus x plus 1. You may want to review that if you don't remember anything about difference of cubes or sum of cubes. It's usually assumed that students at this level of math are familiar with those factoring patterns. Okay, so if you take all the work that's been done here and put it all back together again, what we found is that p of x could be written as x squared, was the first thing I factored out, times, and then all this other stuff is worked out to be x minus 1. Remember, we divided by that, times x minus 4. I changed the order, so it brought the x minus 4 ahead, the x plus 1, and the x squared minus x plus 1. The x squared minus x plus 1 is an irreducible quadratic. Irreducible means pretty much the same thing as prime. It can't be written as a product of linear factors in terms of rational coefficients, and in this case, even real number coefficients. But there's another quadratic here, x squared, but there is really a difference between the x squared minus x plus 1 and the x squared here, although they're both quadratic, and I'll get to that here in a few moments. But before I do that, I just want to point out that if you look at the degrees here we have x squared, which was factored out, which has degree 2. And we have 1, 2, 3 different factors that have our linear or first degree. That gives us 3 more, so 2 plus 3 would be 5. And the quadratic is second degree, so there's all the degrees of our polynomial. It's 7th degree. And you should at some point go ahead and multiply all this stuff out to see that you get back to the original p of x, the 7th degree polynomial I started with here. But I'm not going to scroll back to look at that right now. Okay, so continuing with this. We already know something about the zeros. We found out the 0 was a 0, and 1 was a 0, so those were kind of things that you might discover just by trial and error. After doing some division, found out that 4 was a 0. It also turns out that -1 is a 0, because here we have an x plus 1 factor, so if x is -1, we'd have -1 plus 1, that would be 0, the whole thing would go to 0. And so I sort of put all that together here. 0, 1, 4, and -1 are all zeros, so those are the 4 zeros we know about. And I also did another thing here. See, we've got x minus 1, and 1 is a 0. X minus 4, and 4 is a 0. X plus 1, which could be x minus -1, and -1 is a 0. And then just to be consistent with that, I wrote the x squared as actually being x minus 0, the whole thing squared. And that's just to emphasize that 0 is a 0, just like 1 and 4 and -1. we don't know anything about the zeros that come from the x squared minus x plus 1, at least not just yet. That'll be the next step here. Okay, so moving on. If you look at the x squared plus minus x, it's going to be x squared minus x plus 1. It's an irreducible quadratic factor. Again, not to be confused with this quadratic factor, because this one is actually just x minus 0 times x minus 0. It can be reduced. It can be written as x times x, or x minus 0 times x minus 0. This one cannot be in terms of real numbers. The x squared minus x plus 1 cannot be written like this. So if you took, for example, x minus 1 and x minus 4 and multiplied them together, that would give you a second-degree polynomial. And that one factors, because you just reverse the steps to get back to the factorization. Or you could take x minus 4 times x plus 1. That would give you a quadratic. So there's various ways you can create quadratics out of these different factors. But x squared minus x plus 1 is in a significant way different from those. It doesn't have any real solutions, whereas here we have real solutions of 0, 1, 4, negative 1. Okay, so to see that, we can use the quadratic formula. So if I set x squared minus x plus 1 to 0 and solve that, cannot use factoring, could complete the square, that would work, but I'd prefer to use the quadratic formula in this situation. It's easier, quicker. So all the coefficients are 1 or negative 1. The A is 1, B is negative 1, C is 1. So I plugged all that in here. The opposite of B, opposite of negative 1, square of B, square root of negative 1, minus 4 times A times C, 4 times 1, all divided by 2 times 1. Just to remind you if you hadn't worked with the quadratic formula for a while. Okay, so anyway, a lot of those just become 1. And so we have 1 plus or minus the square root of 1 minus 4 all over 2. 1 minus 4 is negative 3. So we have, the way I wrote this is okay, but normally we want to simplify. If we have a radical of a negative, we want to simplify that by introducing the magical number I, the so-called imaginary unit. So instead of writing the square root of negative 3, I wrote square root of 3, that times I, and then I actually separated this into 2 parts. So this represents actually 2 different complex numbers, what are called complex conjugates. 1/2 plus radical 3 over 2 times I, and 1/2 minus radical 3 over 2 times I. Those are, because they just differ in terms of one has a plus imaginary part, one has a minus imaginary part, they're referred to as conjugates in that case. And it turns out that for the sorts of polynomials we're working with, if one complex number is a 0, then its conjugate will also be a 0. Okay, so if I take those, I can then really complete the factorization. P of x is equal to the x squared we already saw, times x minus 1 times x minus 4 times x plus 1. We had all those previously also. And the quadratic, I actually factored it here. You don't have to spend too much time staring at this and trying to make sense of it. It might cause headaches, I don't know. So, but we have x minus the complex number and x minus the complex number. And those 2 complex numbers are the conjugates that we had, the plus radical I minus radical I. And so this is just for completeness so we can see. So this, again, I could write the x squared as being x minus 0. I don't have a whole lot of space here. And then we have x minus 1, x minus 4, x plus 1. So they're all being written out in kind of the same format. We have 4 real zeros, 0 from x squared, 1 from x minus 1, 4 from x minus 4, negative 1 from x plus 1. So those are the 4 real zeros. And then we have these 2 imaginary zeros. Now for graphing purposes, the imaginary zeros don't play a role. But they are kind of important in the fact that they give us a complete complement of 6 zeros. 1, 2, 3, 4, 5, 6, counting the 0, 0. And actually, mathematicians have a kind of a funny way of counting this, where they say, okay, well, if you wrote x squared out, you could write x minus 0 and x minus 0, like I did up here. in this place. I didn't actually write x minus 0 times x minus 0, but x minus 0 squared means that. And if you think of it from that perspective and made everything kind of the same sort, then we would have two different factors there. Well, actually, we'd have two factors that were identical. They're not different. They are different in that there are two of them. So they're like twins, I guess. So from that perspective, we actually count 0 twice. And it does make a certain sense. You can choose to not like it or think it makes no sense, and mathematicians are just counting in a weird way. And it probably won't hurt you any if you want to think that way. But if we take that way of counting, then we have 2, 3, 4, 5, 6, 7 different zeros here. We have 7 zeros here. They're not different because we have a repeated root. The repeated zero, these are also often referred to as roots. So we have 7 roots, 7 solutions to the equation p of x equals 0. 7 zeros if you count the 0 of 0 twice, but only 4 x-intercepts, as we'll see here in a moment. We refer to that as multiplicity. So the multiplicity is 2 here. The multiplicity for these three factors, x minus 1, x minus 4, and x plus 1, those multiplicities are all 1. The important thing is whether multiplicity is even or odd. When you look at the graph, if the multiplicity is even, the graph will touch the x-axis at that point, but will not cross it. And if you have an odd multiplicity, as we see here, it will cross at that point. The complex numbers don't matter. The zeros involving the complex numbers, those factors don't matter because what their multiplicity is, because they don't show up on the graph anyway in terms of x-intercepts. Anyway, so the next step is to go ahead and do a different screen share here and look at GeoGebra. And here is the polynomial f y equals, it's not written up here in terms of p of x, 7th, 6th, 5th, 4th. Well, that's not right. There's got to be more to it than that. Well, there it is. Okay. If I scroll down, it shows up the rest of it. I could maybe make that box bigger and show the whole thing also. Anyway, it is all there. X to the 7th minus x to 5x to the 5th plus 4x to the, let's see, so x to the 7th minus 5x to the 6th plus 4x to the 5th plus x to the 4th minus 5x cubed plus 4x squared. Hopefully that's all right. Finding a screen where you get all the information you want is a bit of a challenge. This looks like a vertical line here, and this is not a vertical line, but it's awful steep. But if we were to zoom back, we might start to get a sense of the fact that as you go to the left, it goes down. This one looks like it's just going down, but actually it does not only go down, but goes to the left as we're going this way. And as you go to the right, it goes up. Again, it looks almost like it's going straight up. It really isn't. If you were to go out here to x equals 22 and go up, you would eventually run into the function. But it may be way up there. It may be billions of units up there. I have no idea. You could calculate it. It wouldn't take that long, but not really what I'm interested in right now. What I'm interested in is looking at the zeros. So in graphs, we're typically going to want the y-intercept and any x-intercepts. The y-intercept we actually get kind of free of charge here. If you plug in x equals 0, you get the y-intercept, which turned out to be 0. And notice here, 0 had a multiplicity of 2, which is an even number. And because of that even multiplicity, it touches the x-axis but does not cross. Whereas our other zeros, which were at -1, at least the real zeros, -1, +1, and 4, they all had an odd multiplicity of 1, and the graph does cross at those points. We can see here 3 turning points, 1, 2, 3. I do not know whether there are any more. Mentioned earlier there could be as many as 6. Well, actually, I know there has to be at least one more, right? Because we can see the graph going down here and going up there, so there has to be another one someplace. So if you zoom back, zoom back, zoom back, even with all this wonderful technology, still can't find it. Oh, looks like it might be right around there someplace. Somewhere in the general vicinity of y is negative 650. And x is probably not much more than 10, 15. If you have the time and the inclination, I'll leave it to you to go hunting around. One thing is clear, you get a much different perspective depending upon the viewing window you're looking at. Anyway, I don't know how long this has been going on, but I think that was enough information for one video, and thank you for watching.